All right, let's dive right into this explainer. Today, we're taking a seriously fascinating journey under the hood of Bitcoin. We're going to trace the evolution of Bitcoin wallets, starting from the incredibly messy, chaotic early days of managing raw cryptographic locking scripts, all the way to the elegant, near infinite mathematical tree structures that power modern crypto storage. If you've ever found yourself wondering how a simple list of 12 words can somehow control a literal fortune in digital assets across multiple blockchains, well, you're in the exact right place. So here's our roadmap for today. We'll start with the anatomy of an address, then look at the absolute backup nightmare of the early days. From there, we'll break down BIP-32 and the seed tree, contrast hardened versus normal derivation, explore the BIP-44 filing system, and wrap it all up with a master key summary. Let's get to it. All right, section 1, the anatomy of an address. Fundamentally, an address isn't just some random account number or a simple destination. It's actually a user-friendly shortened encoding of a raw locking script. When you hand someone an address, you're literally giving them specific mathematical instructions on how to lock up the Bitcoin they're sending you. And crucially, unlike those raw, clunky scripts, modern addresses have built-in checksums for error detection. This means if you accidentally fat finger a single character, your wallet catches it immediately, stopping you from sending your funds into a digital black hole. Pretty crucial, right? Now, historically, these mathematical instructions have evolved quite a bit. Back in 2009, Satoshi designed the original addresses, starting with a 1 using a format called base 58. Those were for pay-to-public key hash scripts. Then around 2012, we saw the 3 prefix introduced for pay-to-script hash. But as Bitcoin leveled up, the addresses had to level up too. Fast forward to 2016, SegWit rolls out the BIP-32 format starting with BC1Q. This was a huge upgrade, getting rid of case sensitivity and greatly improving those error-checking checksums. And most recently, in 2021, Taproot gave us the BC1P prefix using BIP-32M. But here's the kicker. Despite looking totally different on the surface, every single one of these is really just a clever wrapper for a locking script. Moving right along to section 2, the backup nightmare. Okay, so you've got these addresses to receive money, sure. But how on earth do you manage all the private keys needed to actually unlock them? Man. Historically, this was a massive headache. Imagine being an early Bitcoin user. The original Bitcoin reference client generated completely random, independent private keys for every single transaction. To try and stop you from losing access to your future funds, the software cached a pool of 100 reserve keys. But here's the catch. Every time you transacted, you burned through those keys. After 100 transactions, your wallet would just generate new ones, which meant your old backup file was suddenly useless. You had to constantly, manually back up your wallet file. If your hard drive crashed and you hadn't backed up recently, poof, your money was gone forever. It's exactly why you hear those crazy horror stories of early adopters desperately digging through city landfills looking for discarded hard drives. It was highly stressful and, frankly, incredibly inefficient. Which brings us to section 3, BIP-32, or the seed tree. Everyone in the community knew this constant backing up nightmare wasn't sustainable. We desperately needed a better way. And that leads us to the technical breakthrough that solved the backup problem once and for all, BIP-32. Introduced in 2012 by Peter Wu, BIP-32 is the gold standard for hierarchical deterministic or HD wallets. Now the magic word here is deterministic. Instead of generating completely random keys every time, a single master seed acts as the starting point to mathematically generate all future keys. Because the math works the exact same way every single time, one single backup recovers your entire wallet, no matter how many thousands of addresses you've spun up over the years. Let's look at exactly how this sorcery begins. You start with a random seed, just a piece of data, usually between 128 and 512 bits. This seed is processed through a cryptographic function called HMACSH512. The output of that is a 64-byte sequence that gets sliced perfectly in half. The left half becomes your 32-byte master private key, and the right half becomes your 32-byte master chain code. I want you to picture this combination as the glowing, beating central core of your wallet. From this one single core, literally near infinite branches of child keys can sprout. Next up, Section 4, hardened versus normal derivation. Now that we have this master key, how do those branches actually grow? Well, we need to dive into the mechanics of derivation. Specifically, the really important security differences between the two methods, normal and hardened. The crucial thing to understand here is the trade-off. In normal derivation, the child key is generated using the parent's public key along with the chain code and an index. This is incredibly flexible because it lets you generate new public addresses without ever exposing the private key. But there's a huge risk here. If a hacker somehow gets a hold of just one child private key plus the parent chain code, they can mathematically reverse engineer the parent's private key. Boom. That whole branch of your tree is completely compromised. Hardened derivation fixes this exact problem. It uses the parent's private key to derive the children. This completely severs that mathematical link going backwards. Even if a hardened child key is totally exposed, the parent key remains absolutely 100% secure. Think of it as a firebreak for your funds. Now, because of the clever math behind normal derivation, we actually get one of the most powerful tools in all of Bitcoin, the extended public key, or XPub. This is a 78-byte structure containing a public key and a chain code. Just think about what this means for a business for a second. A merchant can slap an XPub onto their web server, and that server can instantly generate thousands of unique, fresh receiving addresses for every single customer checkout, perfectly preserving user privacy. But because the server only holds the XPub, it literally cannot spend a single Satoshi. If that server gets hacked, the hacker gets zero spending power. The actual private keys are just chilling safely offline. All right, Section 5, BIP-44, the filing system. Okay, so BIP-32 gives us the ability to generate this massive, infinitely expanding cryptographic tree of keys. But let's be real, an infinite tree is totally useless if you can't actually find anything in it, right? That is exactly the problem BIP-44 solves. It's the ultimate filing system for your wallet. It dictates exactly what each branch of the BIP-32 tree is supposed to represent. By enforcing this standard hierarchy, it prevents absolute wallet chaos and ensures that if you take your seed phrase to completely different wallet software years from now, all your funds, all your accounts, and all your histories will be discovered exactly as they were. So here is how a specific derivation path is built, step by step. First is purpose. This is set 244, telling the software, hey, we're using this specific standard. Second is coin type. Bitcoin is 0, Ethereum is 60. This keeps totally different blockchains completely isolated from each other. Third is account, allowing you to separate your funds into, say, savings, checking, or business branches. Now notice those first three steps use hardened derivation. You can tell by the little apostrophe. So they get that strict security isolation we talked about. Step 4 is the change level, which splits public receiving addresses from internal change addresses. And finally, step 5 is the address index, just sequentially counting up, address 0, address 1, address 2. And just to make sure you never lose anything, wallets use something called a gap limit of 20. When the wallet is scanning this path, if it sees 20 unused addresses in a row, it basically says, all right, I guess we've reached the end of the transaction history here, and it stops looking. Pretty smart. Finally, Section 6, the master key summary. We've waded through a ton of deep cryptography today, I know. But what does this actually mean for the everyday user like you and me? Let's ground this in reality. These standards, BIP-32 and BIP-44, literally transformed Bitcoin from a super cumbersome system of individual key backups into a streamlined, highly secure financial command center. You can run watch-only wallets to track balances completely securely using those XPubs. You can maintain strict account separation for your personal and business expenses without ever needing a second wallet. You get seamless multi-device coordination, meaning your desktop and mobile wallets stay perfectly in sync without ever communicating with each other just by deriving the same math path. And finally, cross-chain custody. One single seed phrase controls your assets across Bitcoin, Ethereum, Litecoin, you name it, with zero overlap or risk of cross-contamination. I want to leave you with this final thought. A single seed mathematically guarantees absolute control over a near infinite cryptographic universe. Think about the sheer scale of that for a second. We went from frantically saving 100 random keys to a fragile computer file to a system where just 12 simple words can perfectly organize, discover, and protect unlimited wealth across entirely different blockchain networks. That is true, unadulterated financial sovereignty, all elegantly structured by mathematics. Which leaves us with a fascinating question to ponder as we wrap up this explainer. If 12 simple words can now hold the wealth of a nation and make traditional banks entirely optional, how is this kind of mathematical sovereignty going to reshape the global balance of power? Thanks so much for joining me.